This is a sorted linked list. I want you to search it in O log n time. And your gut says that's impossible, right? Linked lists don't have random access. You can't jump to the middle, so binary search is out. And the best you can do is walk it node by node, O of n. That instinct is correct, by the way. For a plain linked list, it really can't be done. But you can get log time out of one if you build something on top of it. And how we get there is one of my favorite stories in computer science. Because first, we're going to build something perfect. Then a single insertion is going to break it completely. And then we'll fix everything with a coin flip.
I'm not going to tell you the name of the thing we're building. By the end, you won't need me to. You'll have invented it yourself. Some of you already know exactly where this is going. Stay anyway. Knowing the answer isn't the interesting part. The interesting part is watching every other idea fail first. And you'll realize you already use it. It's inside Redis. It's inside systems your apps talk to every day. You've probably triggered one today without knowing it.
Let's pin down the real problem here, because it's not just that search is slow. If you want to store values in sorted order, you've basically got three options, and every one of them makes you pay somewhere. Option 1, a sorted array. Search is great. Binary search, O log n, done. But now insert something in the middle. Everything after it has to shift over by one slot, and that's O of n. Option 2, a linked list. Inserting doesn't need any shifting. Once you know where the new value goes, you redirect a couple of pointers and you're done. That part really is constant time. The catch is the phrase, once you know where it goes, because finding that spot is a search, and search on a linked list is the O of n problem we started with. So a sorted linked list has exactly one weakness, search. And if you think about it, that's a promising sign. Fix search, and the cheap inserts come along for free. Option 3, a balanced search tree. A red-black tree, an AVL tree, these actually give you both. O log n search, O log n insert. But you pay in complexity, rotations, balance rules to maintain on every insert and delete. Anyone who's implemented one from scratch knows how easy it is to get subtly wrong.
And yes, in practice, you don't write one by hand. You import it, and someone else has already dealt with the complexity. But keep that complexity in mind. Near the end of this video, it explains a strange gap in a standard library you've probably used. So that's the deal everyone just accepts. Fast search, fast insert, simple to build. Pick two. Here's my plan. I'm not going to touch the linked list itself because that's a dead end. With only next pointers, there is no way to reach the middle without walking there. No trick fixes that. Instead, I'll keep what the list is good at, cheap local inserts and simple pointers, and I'll build upward. We add the smallest amount of structure that buys us log time search, nothing more. And whatever we're holding at the end will not be a linked list anymore. It'll be a new data structure, one that actually breaks the trade-off. The array does one thing we badly want. It reaches the middle in a single step. A linked list can't have that. So let's ask a cheaper question instead. Okay, the whole problem is that we walk past every single node. So let's just not. We add a second layer. On top of our list, we build another linked list, but this one only contains some of the nodes. Say every fourth node. Think of it like an express train. The local train below stops everywhere. The express above only stops at major stations. And now searching works differently. You ride the express as far as you can without passing your target. The moment the next express stop would overshoot, you drop down to the local and walk the last few nodes. Let's put actual numbers on this. Say the express line has a stop every k nodes. A search takes some express hops, about n divided by k of them, plus at most k walking steps at the bottom. So roughly n over k plus k. And now it's a balancing act. Make K tiny and the express barely helps. Make K huge and that final walk at the bottom gets long. The sweet spot is where the two costs are equal, and that happens when K is the square root of n, which puts the entire search at about 2 times root n. Stop and think about what that means. 1,000,000 nodes. Walking is 1,000,000 steps. Add 1 express layer with a stop every 1,000 nodes, and a search is roughly 2,000 steps. 1 extra layer, 500 times faster. That's a real improvement, but you can already feel the next question coming, can't you?
Why stop at 1? Because look at the express layer. It's just a sorted linked list, which means it has the same problem the original list had. Searching it takes time proportional to its length. But we already know what to do about that, don't we? Put an express line on top of the express line. A third layer, holding only some of the second layer's nodes. 1 layer got us to n to the half. 2 layers gets n to the 1/3. 3, n to the 1/4. Every new layer helps again. And the cleanest version of this is where each layer keeps half of the layer below. Then each layer halves the node count. And if you keep halving 1,000,000, you hit 1 in about 20 steps. So the number of layers is log n. And on each layer, you only walk a step or 2 before you drop down. We did it. About 20 layers, a step or 2 on each. The search that used to be 1,000,000 steps is now a few dozen moves. That's O log n, on top of a linked list. And look at this thing. It's a pyramid. The bottom layer has everything, then half, then a quarter, all the way up to a top layer with 1 or 2 nodes that can cross the entire structure in a single jump. Perfectly balanced, perfectly fast. It's also completely broken. We just can't see it.
Quick detour, because some of you are already shouting a different idea at the screen. Instead of demanding exactly every second node, you could let each section of a layer hold a flexible number of nodes, a minimum and a maximum. When a section gets too full, split it in 2 and promote a node up. If that sounds like a B tree to you, congratulations. It basically is one, and it's a good answer. It's the answer inside most databases. But look at the price. Splitting, merging, checking limits on every single change, that's the same careful balancing work we were trying to avoid, just in a different form. So I'm setting this idea aside on purpose, not because it's wrong, because we're looking for something simpler. Keep it in mind though, it's gonna come back more than once.
So here's what I've been hiding. Everything so far assumed the list never changes. But changing cheaply was the entire reason we picked a linked list. So let's insert 1 value and watch what happens. Remember, the structure depends on a precise pattern. Every second node is on layer 2. Every 4th node is on layer 3. That exact spacing is the only reason the math works. Now insert 1 new value near the front. Every node after it just shifted position by 1. The node that was 2nd is now 3rd. The node that was 4th is now 5th. So the node that's supposed to be on layer 2 is no longer the one sitting on layer 2. The pattern is off by 1, and it stays off by 1 all the way down the list. And to repair it, you'd have to reassign the layer of essentially every node past the insertion point. 1 insert. O of n cleanup. Notice, splicing the new node into the bottom list was cheap. That was never the issue. The layers are the issue. We built a search structure that's fast as long as the data never changes. Change 1 thing and the maintenance costs as much as the slow search we were trying to avoid. We didn't beat the trade-off. We just pushed the O of n from search over to insert. Okay, so patch it. What if we only repair the area near the insertion? Doesn't work. The shift travels all the way down the list. Nothing about it stays local.
fine, then what if we let the structure drift out of shape and rebuild the layers every so often? Now search gradually gets worse between rebuilds, and each rebuild is one big, expensive pause. Also bad. And if your next thought is, okay, be smarter about it. Stop demanding the exact pattern. Give every gap an allowed size range, and repair a region only when its gap breaks the rules. That actually works. But listen to what you're describing. Gap limits, splits, promotions. That's the B tree again. Every deterministic repair anyone has found eventually turns into machinery of that same kind.
So this is where we stand. Demand the exact pattern, and one insert costs O of n, because every node's layer depends on its exact position among all the others. Relax the pattern with rules and repairs, and you're back at the B tree, doing the bookkeeping we were trying to avoid. The perfect pyramid is dead. But look closely at why. In every version so far, the layers are maintained deliberately. A rule picks which nodes go up, and repair work keeps that rule true as the data changes. So here's the strange question. What if we didn't pick at all?
Go back and look at what the layers were really doing for us. We never needed exactly every second node. What we needed was for the layers to thin out at a steady rate, around half the nodes reaching layer 2, around a quarter reaching layer 3, an eighth on layer 4. Which specific nodes got promoted never mattered for the speed, only the proportions did. We obsessed over one exact pattern, when the math only ever needed a rough shape. So the real question was never, how do I maintain a perfect pattern under inserts? That's hopeless. We just proved it. The real question is this: how do you keep those proportions, half, quarter, eighth, true forever, while the data keeps changing, without any node ever checking with any other node? Say it like that, and the answer is sitting right there. Because there's exactly one tool in computing whose whole job is producing reliable proportions with zero coordination. One idea left, and it fits in 3 lines of code.
When a new node arrives, we don't calculate its height. We don't look at its neighbors. We don't even look at its position. We flip a coin. Every node starts on layer 1. Flip. Heads, it gets a layer 2. Flip again. Heads again, layer 3. Keep flipping until you hit tails, then stop. That's the node's height, decided by pure chance. And here it is in code, as promised. Layer equals 1. While a random number is below 0.5, add 1 to the layer. Return the layer. That's it. 3 lines. The entire balancing algorithm of this structure is a while loop. Real implementations just add a cap on the height, 30-something layers, which is enough for billions of entries. Now, here's why this isn't madness. Look at what the coins produce across the whole list. Everyone is on layer 1. About half get heads and reach layer 2. Half of those reach layer 3. A quarter, an eighth, a 16th. That is exactly the shape the perfect pyramid had. We're not building the pyramid anymore. We're letting it form on its own.
Let me run a real search through it so you can see it holds up. Start at the top left on the highest layer. Move right as long as the next value doesn't pass your target. When it would, drop down 1 layer and keep moving right. Overshoot, drop. Overshoot, drop. When you reach the bottom layer, you're standing on your value, or exactly where it would be. How many steps was that? Well, on any layer, you only walk about 2 nodes on average before dropping down, because the layers above have already covered most of the distance. 2-ish steps per layer, about log n layers. O of log n expected. That million node search still lands in the same few dozen ballpark the perfect pyramid promised. We lost nothing. But now, run the same insertion that broke everything before. A new value arrives. Flip its coins. Say it comes out 2 layers tall. Find its spot, which is just the search we were doing anyway, and remember the last node you visited on each layer on the way down. Then, link the new node into its 2 layers. Done. No shifting, no ripple, no reassigning layers across half the list.
No other node changes, because no node's height ever depended on any other node's position in the first place. That's the whole trick. There is nothing to re-coordinate, because nothing was coordinated to begin with. And deleting works the same way. Find it, unlink it from each layer it's on, done. All local. 2 honest footnotes. First, the cost. The average node is about 2 layers tall, so we're storing roughly twice as many pointers as a plain list. The values themselves aren't copied. It's a constant factor, still O of n space. Second, the worry you should have. I keep saying on average. Can this go wrong? Could every node get tails immediately, leaving the whole thing flat and slow? Yes, technically. It's just so absurdly unlikely that for any realistic size, you will never see it. That risk is smaller than failure modes you already ignore every day. In practice, this behaves like a balanced tree, minus the rotations, minus all the rebalancing code. We gave up the exact pattern. In exchange, we got the thing the exact pattern could never give us, a structure that stays fast while it changes. So look at what you're holding. A linked list still in sorted order. Extra forward pointers stacked on top in layers that thin out as you go up. You search from the top, moving right and dropping down. You insert with a coin flip. Fast search, fast insert, no rotations, no rebalancing, and no global coordination anywhere. It started as a linked list. It isn't one anymore. What you just built is called a skip list, and the name is exactly what it does. It's a list that skips. William Pugh published it in 1990, and the title of his paper says everything. Skip lists, a probabilistic alternative to balanced trees. A probabilistic alternative. That's the whole idea in 2 words. A balanced tree enforces its shape with strict rules and rotations. A skip list enforces nothing. Randomness produces the shape on its own, and we accept almost always fast instead of guaranteed fast. Oh, and if you're wondering whether you could pull this off without randomness, you can. Deterministic skip lists exist, but remember how back in the catastrophe, every smart repair kept turning into the same machinery? That's not a coincidence. Every known deterministic version is built from exactly that. Gaps, splits, bookkeeping, relatives of the B tree. There it is again. And you know what? Knowing the name is the boring part, because this thing is running inside products you use today. And one of those stories involves 10 million players, a live leaderboard, and a trick we haven't covered yet.
You're playing an online game.
10 million players. In the corner of the screen, there's a live leaderboard, and it knows your exact rank. Number 4,183,772. Scores are changing constantly, thousands of updates a second, and your rank stays current the entire time. Stop and think about how you'd build that. A sorted array? Every score update shifts everything. Unusable at this scale. A hash table? It finds any player instantly, but it keeps keys in no particular order. That's the whole point of hashing. So it has no idea who's ranked where. A balanced tree? We're getting closer. But there's a simpler answer, and you already invented it. Odds are that leaderboard is Redis. And a big sorted set in Redis is a skip list underneath, paired with a hash table so you can also look up any player instantly. Which means I can pay off the promise from the very start of this video. You have used a skip list, probably today. A score changes? That's a delete and an insert. Both log n, both local. The rank is the interesting part. Store one extra number on each forward pointer. how many bottom layer nodes that jump skips over. Now walk the normal search path from the top and add up the numbers on the jumps you take. By the time you reach the player, that running total is their rank. Log n even with 10 million players. And notice what else you get at no extra cost. The bottom layer is still a plain sorted linked list, so reading your data in order is trivial. Range queries too. Everything between 50 and 90, search for 50, then walk right along the bottom until you pass 90. Log n plus the size of the answer. A hash table can't offer any of this because it doesn't keep order at all. Here, the entire structure is built on it.
And it's not just Redis. LevelDB and RocksDB, storage engines under a lot of modern infrastructure. Every write lands first in an in-memory buffer that has to stay sorted under a constant stream of inserts. By default, that buffer is a skip list. When it fills, RocksDB writes it out to sorted files on disk, arranged as what's called an LSM tree. A story for another day. But look at the classic databases, MySQL, Postgres, SQLite, and their on-disk indexes are B trees. Because on disk, the calculus flips. Following pointers one at a time is extremely slow there, and the B tree's page-sized nodes match exactly how disks read data. So in practice, the work is split. B trees and their relatives handle disk. Skip lists handle memory. The B tree was never a wrong answer. It was the answer to a different question. And that's the last time it comes up today.
Then there's Java. And here's the strange gap I mentioned near the start. The standard library ships a concurrent hash map and a concurrent skip list map. There is no concurrent balance tree in there at all. That's not laziness. Keeping a balance tree correct under many threads is brutal, because one insert can set off rotations that cascade up the tree, moving nodes around while other threads are reading them. A skip list insert changes a few pointers in one small neighborhood. That's exactly the kind of change you can make thread safe efficiently. Not trivial. Nothing concurrent is trivial, but feasible in a way that rotating trees just isn't. For ordered data shared across threads, the skip list became the standard choice. Even search engines. Lucene, the engine inside Elasticsearch, keeps skip pointers over its lists of matching documents, so a query can jump over huge blocks of documents that can't possibly match.
One last thing. The coin wasn't a one-off. It's a pattern. Randomize an unordered set, you get a hash table. An ordered one, a skip list. A search tree's shape, a treep. 3 structures, 1 move. In computer science, randomness isn't what you settle for, it's what you reach for. And notice the shape you ended up with. Mostly short links, a few long jumps. That's the same idea behind 6 degrees of separation. A few long-range connections are enough to cross a huge network in a few hops. There, it connects people. Here, it connects data. But here's what actually matters. You didn't memorize any of this today. You derived it, dead end by dead end, all the way to a structure that runs Redis. That's the skip list, invented in 1990, and just now, reinvented by you.